Welcome to the session. It's version control and then programming. So my name is Sung Kim, and then I'll be the session chair of this wonderful session. We do have 6 wonderful talks, and then also we have very, very good presenters. The first talk is about the fixing upstream merge, and then Chung Ha from USC will talk about it. Let's welcome our first speaker.
Thank you for the instruction. For the screen. So can you see the screen?
Yes.
Okay, let's get started. Hello everyone. My name is Chung Ha Song from USC, working with Cha Wang. And I'm going to present a study of upstream induced merge conflicts and its fixes in divergent forks. This is joint work with Shivendu, Mike, and Pallavi from Microsoft. A divergent fork is created by a fork, and it is widely used for customization and independent development by saving a lot of effort without starting a project from scratch. For example, Android OS is customized by different device vendors. In divergent forks, we call upstream for an original project and downstream for a project created by a fork. One of the most popular examples is a Chromium-based web browser. There are many web browsers forked from Chromium. To understand divergent forks, we use data from Microsoft Edge development process, but we do believe this study will help to understand the nature of divergent forks. Then what is the problem of these divergent forks? Since they are forked from original projects, we need to regularly merge the changes from upstream for important updates, such as security patches and feature changes for compatibility. However, the problem is this merge causes conflicts like build breaks or test fails. Let me use a simple example with a commit of Microsoft Edge. Let's say Edge is released in April, and after some time during May, the Edge team noticed Chromium made some security updates. So the team tries to pull the changes by a merge from the recent Chromium. And during this merge, we encounter a build reg because of the changes from the upstream. It says a function call of selected index is an undefined symbol in this file. Then an engineer tries to figure out the problem by looking at Chromium's commit history. As the source code cannot be built, it usually takes from several minutes to hours, depending on situations. Finally, the engineer finds the function definition of selected index has been changed to get selected index in a commit history, and a corresponding function call change. So the engineer updates the Edge code accordingly. And this kind of fix happens several times more to actually build the code. Based on our data, there are more than 25,000 commits made in Chromium for 3 months. And it is necessary to merge since it may have important updates. But it consumes a lot of engineering work when upstream code frequently updates like Chromium. Due to the reasons, we found out many Chromium-based web browsers are behind around 1 to 8 versions from the recent Chromium. So what is the ideal way to save this cost? Here is what we think. First, we have a build reg on a specific file, and we provide a magical autofix feature. And by clicking this button, it automatically updates the code. Also, it provides the root cause of the build reg. Then everyone will be happy as we save a lot of engineering cost. But is this even possible? To answer this, our work has 2 contributions. First, we understand the nature of merge-related conflicts in divergent forks by studying them. Second, we provide a prototype tool for fixing the merge-induced build regs with an AST-based auto patch and input commit pruning. Finally, we check the feasibility of this tool by applying it for real conflicts. Here is an overview of the simplified structure of the Edge development process. The dashed lines show branches from top to bottom: upstream, integration, stabilization, and downstream branch. And each dot shows a commit made by each branch. This red dashed box shows what happens every merge. There are two branches involved during this merge: integration branch and stabilization branch. All merge-induced conflicts are resolved in these two branches. And finally, the buildable version is merged back to downstream. Here's the distribution of fixes we studied from stabilization branch and integration branch. It has three categories: texture conflicts, build breaks, and test failures. Among these, we target build breaks for automatic patches. The reason is the build breaks cost a lot of effort of engineers, as they need to look up the history of upstream changes. And we further categorize the types of build breaks based on causes and fixes. Based on the study, we provide an automatic patch procedure as shown in this figure. First, I'm going to talk about AST-based automatic patches. The procedure is from two versions of files of upstream. We diff the ASTs of them and infer possible patches. Then we apply the patches to downstream files. We infer patches by checking definition changes and use changes between two ASTs. For example, here, AST diffs the two ASTs and shows the definition of the function name is changed from selected index to get selected index. This shows a use case change where the same name is updated under function call node. Finally, we infer this patch since we have a consistent definition and use changes. With this inferred patch, we apply it to downstream. We search if there is any match in this AST. And we find there is a call with the name selected index, so we apply this change on this node. This AST-based approach seems reasonable, but we have a scalability issue when we just use this approach. As the size of the source code is really large, creating ASTs and diffing ASTs for all files are too expensive, and there are too many commits to consider. So we need to prune the input commits for this AST-based approach. Here is a diagram to describe input commit pruning. Let's say we want to fix a build rec here. Since we are not able to build the source code here, we find the latest compiled version from this point. And this is the latest working version. This version doesn't have change information after we merge. So it has original connection of the symbol name, which was not resolved in the build rec point. Then we use a symbol table of this working version to track the definition of the broken symbol and the file name that has this definition. Next, with the file name we find, we search which commit actually modified this file through this upstream range. This upstream range is between the last commit we merged and the commit we want to merge. In this range, we get specific commits that are responsible for this build rec. Therefore, we effectively reduce the upstream files to consider for this AST-based approach. With this framework, we check the feasibility. On average, our framework could fix almost 40% of the considered commits, and each fix took around 70 seconds, which is much faster than human-driven fix. Also, input commit pruning could reduce the number of commits to consider by 3 orders of magnitude. Here is the conclusion. Our study shows the first industrial case study with Microsoft Edge data to understand the nature of merge-induced conflicts in divergent forks. Based on our study, we categorized the conflicts and provided an automatic patch method for build recs. And our results show this encouraging feasibility by providing an insight into divergent fork development. Thank you for listening to this talk, and please find our paper for more details. And I'm happy to answer any questions.
Yeah, thanks a lot for the great talk. Any questions? So this is very, very impressive. So my question here is that the 40% you can fix automatically, right? But those like conflict, how easy or how hard to fix for human?
We didn't actually measure each fix by human driven thing, but uh, on average, it took like 30 minutes to read even for the simple fixes, if the engineer is not familiar with the code.
Oh, okay. So definitely it's useful to use this tool, right? One question from the audience, it asks that is that possible that the integrator performed additional changes after that merge, and those changes were responsible for the broken build, for example?
Could you repeat the question? Because
Right. So is it possible that integrator can add additional changes during this merge, automatic merge?
integrator,
Yeah,
does it mean the human or
human. I think. Yeah, I think.
yeah? So right now the entire process is not for providing complete set of patches right now, but it's more like a recommendation patches, and people can apply if they want, and some of the patches may not be applicable. So yeah, integrator will get involved during this process.
Okay, so that's great. Let's thank our speaker one more time. Thank you very much.
Thank you.
And then our second talk will be something about information for aging perspective.